Hi, good morning. Welcome to the today's session of Computer Organization and Architecture. We are discussing Module 4. So the Module 4 is the memory system. In Module 4 in the previous class we saw the basics, okay, which are essential to understand how the memory works, okay. So in today's class we are going to discuss about the types of memories that are available in the market. So there are several types of memories that are available, and if you consider the cycle time, so it ranges from 100 nanoseconds to 10 nanoseconds. So we have the cycle time, memory cycle time, which ranges between 100 nanosecond to 10 nanosecond. So depending on the cycle time, so and depending on the storage capacity, so we have different types of memories. And if you consider the VLSI technology, so because of the VLSI technology, now whatever the memories we have, so they are available at cheaper rate compared to the memories which were available in 1960s. So when they invented the semiconductor memories, so the cost was very high. So the whatever we had earlier, the magnetic so disk or the tape, whatever we had earlier, so the semiconductor memory was costly compared to the previously existing memory systems. So but nowadays it has been reduced because of the advances what we have in VLSI technology. So now if you consider the different types of memories, so now there are two important types. So that too, in random access memory we have two important types of memories. So one is SRAM and the other one is DRAM. So now in today's class, so we will be learning about the RAM memories, in that particularly about the SRAM. So before that, let us see the organization of RAM. First we will understand organization by considering a small memory, so that it is easy for us to understand. And if you consider the larger memories, so the organization remains same, only the difference is with respect to the number of address lines and the number of connections required. So that we will see next. So now if you consider the internal organization of memory chips, so how the chips or the cells inside a memory are organized. So let us understand that first. So if you consider each memory cell, so it can hold 1 bit of information. So that we have discussed. So right from the first module, so whenever we discussed about the memory, so we have discussed that so it is capable of storing 1 bit of information. Each cell what we have in a memory is capable of storing 1 bit of information. And so if you consider the organization, memory cells are organized in the form of an array. So memory cells are organized in the form of an array, and so one row is one memory word. So it is organized in such a way that so one row whatever we have, so it is nothing but one word of the memory. And next, if you consider all cells of a row are connected to a common line which is known as the word line. So all the cells of a row, if you consider a row, all the cells which are present in a row, so if you consider a 32-bit computer, we will be having 32 bits in a single row, because we have called it as a word is. So entire the 32 bits whatever we have, so those will be connected to a common line which is known as a word line. And next is word line is connected to the address decoder. So because as we have discussed, so in order to access the memory, in order to perform read or write operation, so we have to have some address. So after assigning the address, so whenever it is required to access the data, it is essential to indicate or it is essential to mention the address of the memory from where we want to read the data or to where we want to write the data. And then if you consider the control lines, so the other control lines what we have in the organization are sense or write. So we will be having a sense or write circuitry to which we will be having two control signals. So one is read or write bar, okay. So that we know what is the function of the read or write bar. So that indicates the direction of operation, whether we have to read or whether we have to write, okay. So that will be decided by the signal which is present on read or write bar, okay, control line. And another control line which we will be having is a CS, that is chip select. So it is going to select one of the chip, okay, in a multi-chip system. So if you have a multi-chip system, okay, memory system, in that case, so to which chip, okay, it is referring to, so that will be okay, present on the CS control line what we have, okay. Yes, so if you observe, we have sense or write circuits that are connected to the data input or output lines of the memory chip, okay. So in order to understand these, okay, let us consider the figure. So what we have, so if you consider the organization of bit cells in a memory, so this is how they are organized. As I said, you can observe here, so we have, okay, a row, so which is nothing but a word, okay, a word of a memory, or you can call it as a memory word. And so this is W0, W1, etc., W15, okay. So we are assuming that this memory is consisting of 16 words, and if you observe in each row we have, okay, so 8 bits. So here it is B0, B1, etc., up to B7. So we have 8. So 16 into 8 is 128 bits. So here we have considered a very small memory. So it is able to store 128 bits of information, and since we have 16 words, okay, so it is sufficient to use address line of, okay, so 4-bit. So if you use, okay, 4-bit address line, it can address all the 16 words what we have in the memory. So we have 4 address lines in order to, okay, and then so if you consider the data lines, so we have 8-bit data, therefore there will be 8 data lines. And in addition to this, so as I said, for sense or write circuit, read or write, sense or write is nothing but, okay, read or write circuit, sensing is nothing but whatever it is, okay, there, oh, that it is going to sense the value which is present, okay, in a cell, so that will be sensed. It is nothing but read operation, okay. So now if you consider the sense or write circuit, we have 2 control signals. So one is read or write bar, okay, and the other one is chip select, okay, CS. So and in addition to these lines, so the other connections what we require are the power supply connections, 2 supply connections, one to the, okay, VDD, and the other 2 are, sorry, other one is a ground connection. So we require 2 supply connections. So totally if you consider, so we have, okay, so 16 external connections. 16 external connections, okay, are required, okay, if you consider 128 bits, okay, storage capacity, okay, 128 bits, okay, so, okay, totally it requires 16 external connections, so for a memory of 128 bits. So now if you observe, so see here we have both, that is bits B7 as well as its complement, both will be there, and depending on, okay, the bits or whatever the, okay, whether it is a read operation or write operation, so this circuit will decide, and it is going to copy that particular bit and it is going to connect it to data input or output lines. Here we have data input or output lines, so this will be connected to the data lines on the bus. So on the okay, bus, as we all know, we will be having control lines, we will be having address lines, and we will be having data lines. So these data input or output lines will be connected to the address line, sorry, the data lines that are there on the bus, okay. And so we have another example here. So organization of a 1K, okay, into one memory chip. So if you consider, okay, 1K K, that is 1024 bits storage, okay, memory. So this can be organized as 128 cross 8. So 128, okay, cross 8. So we have, so 2, yes, we have 1024 bits. So you can organize it. So in the, okay, similar way as we, okay, saw in the previous slide, that is, so this is the way in which, okay, we have organized. If you observe, so we have 128 words, each word containing 8 bits. If you want, you can organize, okay, in this way, or so if you want to organize it as 1K cross 1 memory chip. So in that case, so how will be the connections? And if you consider 1, okay, K cross 1, in that case, what are the, okay, what is the total number of address lines required? Since we have 1K, okay, so in order to represent this 1K words, we require 2 to the power 10, okay, therefore, so 10 address lines are required, okay, and coming to the additional connections. So since we have, see here, since we have 1K cross 1, so the data input output, okay, which is going to be provided out of this circuitry or out of this memory chip is 1, okay, therefore one data line is required in this case. See here, so finally we have only one data, okay, therefore, so we have one data line and 2 control lines and 2 supply lines. So totally we require 15 external connections. So if you organize, okay, the memory of 1K cross 1, okay, memory of 1024 bits as 1K cross 1, then these are the total number of connections required. And in this case, if you observe the 10 address lines what we have, okay, it has been divided into 2 groups, so each of 5 bits. So if you observe here, we have 5 bit, okay, row address. So the row address will be generated by a group of 5 bit and column address will be generated by a group of another 5 bits, okay, address lines. So totally we have 10 bit, but so we have organized this in such a way that, so because we need to select 1 bit, okay, we need to select 1 bit at a time and 1 bit has to be given to the data lines, therefore, so it is organized in such a way that, so we have 2 groups of the address line. So here, since we have 5 bit address line row, okay, so 2 power 5, so it can, okay, generate 32 addresses. So if you observe here, so this is a memory cell which is consisting of 32 cross 32. So it has 32 words, each word containing 32 bits. Therefore, so 32 cross 32 is nothing but 1024. See here, so this is the total capacity. So but the organization what we have done is, so we have organized it in a way that, so it has 32 words and 32 bits. And what we are going to do, we are going to, okay, make 2 groups of the address line such that, so it selects one of the row, okay, one of the row, okay, in 32 rows, and then so those rows will be given as input to output multiplexer and input demultiplexer, so which is present there. So it is a 32 bit output multiplexer and it is a input demultiplexer. Yes, so now the function 32 to 1, sorry, not 32 bit, 32 to 1, 32 is to 1, okay. So multiplexer, it is going to consider the 32 bits of a word, okay, so of the address whatever we have mentioned over the 5 bits what we have, and out of 32 it is going to select 1 bit. So because we have 1K cross 1 organization, so out of 32 bit, depending on the column address, depending on the address which is generated by the other 5 bits, so it is going to select 1, okay, bit from 32 bits. Therefore this is how, okay, the 1K cross 1 memory chip is organized. And if you consider the, okay, organization, that is 128 cross 8, in that case how many external connections are required? So in order to represent 128 we require 7 address lines, then 2 control lines, plus before the control lines we have 8 data lines and 2 control lines, 2 power supply lines. So we have totally 15 plus 4, 19 connections. So if you organize it as 128 cross 8, so this is how we have the total number of external connections depending on the organization. And similarly if you consider the 512K cross 8, let us assume the memory size is 4 megabits. So in that case let us assume we have organized this as 512K cross 8. So if this is the case, then so what is the total number of address line required? And control lines remains the same, and data lines, so we have the information, and then the supply connections whatever we require is same. Therefore just we need to identify how many lines are required in order to address lines are required in order to represent 512K. So all of you take this as an assignment, find out. So if you want to represent or if you want to have 4 mega in an organization wherein we are going to organize, it has 512K cross 8, then how many external connections are required? Find out this. So this is about the memory organization. So that is in general, it is not specifically SRAM or it is not specifically DRAM. This is about the general organization of a memory. And so as I said, if you consider the examples what we have taken, so these are very small memories. Practically we will be having large memories compared to these, but there is no difference in the organization. Organization remains the same. Depending on the size of the memory, only the fact which is going to vary is the total number of external connections, that is the number of address lines, number of data lines, and number of the depending on the size of the memory, only the fact which is going to change is the total number of address lines, total number of data lines. So depending on that, the external connections will vary. Other than that, the organization for the larger memories what we have in the available computers, in all the available computers remains same. So this is about the organization of a memory. And as I said, so the basic types what we have when we consider a memory are the SRAM, static RAM and dynamic RAM. And in today's class we are going to discuss about the static RAM. So in the next class, in the next session, so we are going to discuss about the dynamic RAM. So now let us consider the static RAM. Yes. So we have the static memory. So as the name itself is indicating, we are calling this as static because it is able to retain its state only when the power supply is given to the memory. So once we remove the power supply, the contents will be lost and we cannot expect the same content once we give the power supply. Once we turn on the power supply, whatever the contents we have, so we cannot expect it to be same as the previously processed data. Yes, this is about the static memory. Now let us understand so how it is going to store any information. If you consider the static RAM cell, see here, so both are same. Here we have NOT gate representation, there we have NOT gates which are replaced by the transistors, and the type of the transistors are CMOS transistors. So if you consider the RAM cell, see here the two inverters are connected in back-to-back fashion, and this will be acting as a latch. So latch or flip-flop, the function of those is to store the information. So here, so the flip-flops, so here the inverters what we have connected in back-to-back fashion are going to act as a latch. Yes. Now in order to understand so how it is going to store or how it is going to sense. So let us first let us understand, okay, how to read or write, okay, from this static RAM cell, and then let us see so what is the difference, okay, between the static RAM cell and the CMOS memory cell. So difference, as I said before, is only with respect to the implementation. So since we have the NOT gates, so if you consider at the semiconductor level, we will not be having any NOT gates, okay, without the transistors. All, okay, NOT gates, okay, in all the technologies we have the transistors which perform the function of any required gate. Therefore, NOT gates so can be implemented using CMOS technology, or it can be implemented using NMOS, or it can be implemented using, okay, PMOS. So depending on the, okay, implementation type, depending on the transistor type, we will be having, okay, variation in implementation of the inverter. Here we have taken an example of CMOS, okay. Why? Because CMOS are the one which consumes less power. So because of that reason we have considered it as an example, okay. So wherein, so we have replaced the NOT gates using the CMOS inverters. Yes. So if you consider the static RAM cell, so in this you can observe we have B, we have B dash, both are complement to each other, okay, and then we have transistor T1, we have transistor T2, we have X as the, okay, position here or the value, okay, of this particular node, and Y is this node, okay. And so these lines what we have are bit lines, and these lines what we have are word lines. So now, yes, now let us understand so how read operation and write operation is going to work when we consider a static RAM cell. So if you consider the static RAM cell, so we have B, okay, and we have B dash, so which are complement to each other. Then we have two transistors, then we have this node, okay, which is represented as X, and we have an inverter here, and then we have another inverter. Yes, let us represent this as Y, okay, and so here we have another transistor, and transistors are connected to word line, see here, so this is word line, and these are nothing but B and B dash, so these are nothing but bit lines, or just you can represent this as, yes, let this be bit lines. Yes, so I have redrawn the same, okay, circuit here so that we can understand by analyzing the values at different nodes, okay. Since I cannot write there, I have written here. Yes, so now if you consider the state is 1, okay. So let us consider the state of this device, okay, or cell what we have is 1. So now let us understand so how the read operation, okay, sense operation is going to work. So if you want to read, then so we have to, okay, see that so this B contains 1, and that has to be given to the sensor, okay, write circuit, and it is going to give it to the data input or output line, so which will be then connected to the data lines of the bus. So now, so let us, okay, assume that the state is 1. So now what, okay, we are going to do is we are going to activate this line, that is the word line. So whenever we activate the word line, the transistors T1 and T2 will be turned on. So see here, so if this is high, then only the transistors T1 and T2 will be turned on, or otherwise this will be in off state. So whenever we turn on this, okay, or we activate the word line, so this T1 and T2 will be turned on, and okay, so whatever the value we have, so remember, so whatever the value we had stored earlier, that is what we are saying the state as 1. So we will be having X value as 1, okay, and y value as 0. And remember, when we turn on this, so this will become short, and so b will be having a value of 1 and b dash will be having a value of 0. See, so whenever T1 and T2 are turned on, this will become a short, and whatever the values we have here, that is 1, okay, here it is 0, 1 will be copied into B and 0 will be copied into the B dash, okay. So the state, so whatever we have, okay, the state which is represented as 1, so that we have in B. So this will be connected to the sense or, okay, the right circuit, and that circuit is going to check the value and it is going to give it to the data input or output line. Similarly, if you consider the state is 0, okay, even in that case, so remember, if the state is 0, this node will be at 0 and this node will be at 1. Therefore, whenever this transistor is, okay, turned on, so this will be acting as a short and this will be copied here. Therefore, so in that case, if state is 0, in that case B will be 0 and B not, okay, B dash will be 1. So this is how the read operation is going to work. So whatever we have there, so that will be copied into the bit lines, and those bit lines are connected to sense or right circuit. From there it is going to copy, okay, or it is going to send it to the data input or output lines. And next, if you consider, okay, the write operation. So let us assume we want the state of this, okay, let us assume, okay, these values itself, we have 0, okay, at this node, we have 1 at this node, and let us see, so what happens when we write something into the RAM cell. So let us assume we want to write, okay, a value of 1 into this. So in this case, whatever the value we want to write, that will be sent, okay, over the bit lines. So in the previous case, so whatever the node, okay, values we had, those values were copied into B, okay, and those values were, okay, detected by sense or right circuit, and that was given as output. In this case, so if you want to write 1, so this will be sent over B and B dash. In this case, B value is 1 and B dash value is 0. So this will be sent over these lines, and then it is going to activate the word line. So when this is activated, okay, this T1 and T2 will be turned on, and this acts as a short, and it is going to copy the bits which are sent to the X and Y values. So after copying, node X becomes 1 and node Y becomes 0. So this is how the write operation, okay, is going to work whenever we, okay, send the control signal. So depending on the required operation, that is R bar, W bar signal, whatever we have. So depending on that value, so this is how, okay, it is going to store or it is going to read the contents, okay, from the RAM cell. So this is about the working of the RAM cell. So now if you consider the CMOS, okay, memory cell, so as I said, the working remains same, so there is no difference. So whatever we have is CMOS, okay, implementation for inverters. That is the only difference. In this case, if you consider, okay, see here, this T3, T4, T5, T6. So let me write this once again, okay, as it is not clear. So let me write, okay, Yes. So see here, I have redrawn the CMOS memory cell. So here you can observe, so only difference what we have is, we have inverters, okay, NOT gates, which are replaced by CMOS inverters. So now if you consider, this is PMOS, okay, this is NMOS. So this is PMOS once again, this is NMOS. So PMOS transistors, so they will be turned on if you give a 0 to the gate, okay. NMOS transistor will be turned on and when a 1 is given to, okay, the gate. So now if you consider the states as 1 and 0, let us assume X is 1 and Y is 0. So if you assume that, so then you can notice that, so since we have X as 1, okay, this is connected to T6, okay, and see here, this 0 is connected to T3. Therefore, so if this is the condition, then T3 and T6 will be turned on and other transistor will be off, okay. And so whenever we want to copy or whenever we want to replace, okay, the data with the newer value, then we are going to activate this word line depending on read or write bar signal. Whenever it is activated, okay, so the nodal value will be changed. And if you assume the nodes are X is equal to 0 and Y is equal to 1, in this case, so what happens is, so the transistors T4 and T5 are turned off, whereas T3 and, okay, and T6 will be turned off. So these two will be turned on and the other two transistor will be turned off. So like this, so if you consider the operation wise, so whenever we want to read, okay, we are going to make this word line active so that the transistor T1 and T2 are turned on, and then so these two transistors, when it is turned on, the nodal value, okay, depending on the nodal value, it is going to copy, is going to sense. If it is a write operation, so whatever the bits that needs to be written into the cell will be sent over B and B dash, okay, those bits will be copied, okay, and accordingly the latch value will be updated. But remember, so this value will be stored only till, okay, the supply is on. If you consider the VDD, okay, or V supply, whatever I have written here, I have indicated the ground symbol. So if you consider the CMOS inverters, voltage CMOS inverters, so they require a power supply of 5 volts, and the recent or the modern, okay, the CMOS cells whatever we have, so they require an voltage of 3.3 volts. So in this case, so the CMOS inverters or CMOS technology if you use, so those are, so the one which consumes less power, so because of the reason that, so they are not going to, okay, allow the current to flow. Whenever the transistors are on, only then the current will be flowing, and or otherwise, so it is going to make sure that there is no current between the supply and the ground. Only when the transistors are on, then only it is going to, okay, provide the path between the supply and the ground to for the current flow. Other than that, so the current flow will not be there. So because of this reason, so these consumes less power, and CMOS cells are the one which are most widely used. And if you consider the static RAM, as I said, so it is able to store the data only when the power supply is given to the memory chip. So if the power supply is turned off, then as I said, whatever the data, okay, that will be available after turning on will not be the same as the previous. We cannot expect the same, okay, data to be retained by the SRAM. So because of that reason, so we call this as volatile memory, and this is used in cases where we have speed as a crucial issue. So if the required speed is very, okay, high, then only we go for this, and or otherwise, so wherever the storage is essential, even after turning off the power supply to the memory, in such applications we do not choose the static RAM. So static RAM is useful only when the speed is a very important issue. So in that case we choose SRAM, okay, compared to other memories. So this is about the static RAM. So in the next class we will be learning about the dynamic RAM, and we will be continuing the next class. Thank you.